Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on fluids. Let's go ahead and get started with problem number 1. Problem number 1 says object A and B are submerged at a depth of 1 meter in a liquid with a specific gravity of 0.877. Given that the density of object B is 1/3 that of object A, and that the gauge pressure of object A is 3 atmosphere, what is the gauge pressure of object B? Now, the key idea here is that gauge pressure only depends on the properties of the fluid and the depth at which an object is submerged. It does not depend on the object's density. Now, since both objects A and B are submerged at the same depth of 1 meter in the same fluid, their gauge pressures will be identical regardless of their densities. The density of object B being 1/3 that of object A is irrelevant to the calculation of gauge pressure because the fluid's density and depth are the only factors that matter. Therefore, the gauge pressure of object B has to be the same as that of object A, which is 3 atmospheres. So the correct answer for problem 1 is answer choice C. Beautiful, let's move on to problem 2. Problem 2 says, an anchor made of iron weighs 833 newtons on the deck of a ship. If the anchor is now suspended in seawater by a massless chain, what is the tension in the chain? Note that the density of iron is 7,800 kilograms per cubic meter, and the density of seawater is 1,025 kilograms per cubic meter. Now, when the anchor is suspended in seawater, 2 forces act on it. We have the gravitational force. This is the downward force due to the anchor's weight in air, and it's given as 833 newtons. The second force is the buoyant force. This is the upward force that's exerted by the seawater on the submerged anchor, and the buoyant force is determined by the volume of water displaced by the anchor. Now, our goal is to calculate the tension in the chain. The tension in the chain is going to be the difference between the anchor's weight and the buoyant force because the object is in translational equilibrium. So we can write that the tension in the chain is equal to the gravitational force minus the buoyant force. We're given the gravitational force to be equal to 833 newtons. Our goal is to figure out the buoyant force so we can plug it into this equation and calculate the tension in the chain. Now, the buoyant force, this is given by Archimedes' principle, which states that the buoyant force equals the weight of the fluid displaced by the object. So here we have our equation that says the buoyant force is equal to the density of seawater multiplied by the volume of water displaced by the anchor multiplied by acceleration due to gravity. Now, because the anchor is submerged entirely, the volume of the water displaced is going to be equal to the volume of the anchor. So we can go ahead and replace this term with a term that notes the volume of the anchor. Now, we don't directly know the volume of the anchor, so we can't calculate this term. Instead, we're going to replace this term, volume, with mass divided by density, because remember, density is equal to mass divided by volume. If we're trying to calculate volume, volume is just mass divided by density. So we are going to replace this volume of the anchor term with mass of the anchor divided by density of the anchor. And what we get now is that the buoyant force is equal to the density of seawater multiplied by the mass of the anchor divided by the density of the anchor multiplied by the acceleration due to gravity. Now, we also don't know the mass of the anchor. Instead, we're going to replace this term, and we're going to use Newton's second law to do that. Newton's second law says that force is equal to mass times acceleration. If we want to isolate mass and get a definition for mass, it's going to be that mass is equal to force divided by acceleration. And here, we're going to focus on gravitational force, and our acceleration is going to be the acceleration due to gravity. So we're going to go ahead and replace the mass of the anchor with this term. What we get is that the buoyant force is equal to the density of seawater multiplied by the gravitational force divided by the density of the anchor multiplied by the acceleration due to gravity. And that's all multiplied by the acceleration due to gravity. And really quickly, you see that we have acceleration due to gravity in the numerator and in the denominator, so those cancel out. And we're left with the density of seawater multiplied by the gravitational force divided by the density of the anchor. And we actually know all three of these variables, so we can go ahead and start to plug values in. The density of seawater is 1,025 kilograms per cubic meter. The density for our anchor is 7,800 kilograms per cubic meter. And our gravitational force is 833 newtons. Now, to calculate this without a calculator, we're going to do some approximations. We're going to say that 833 is going to be rounded to 800. We're going to round this to 8,000, and we're going to round this to 1,000. So now what we're left with is 1,000 divided by 8,000 multiplied by 800. Notice that kilograms per cubic meter, these units cancel out, and what we're left with is just units Newton. So our final answer is going to have units of Newton. Now, this is going to give us 100 newtons, and this is because we can divide both of these values by 800 to get 1 and 10, and we're left with 1,000 divided by 10. That gives us 100 newtons. Now, be careful here. This is not your final answer. This is just our buoyant force. We need to take this and plug it back into our equation that is going to calculate the tension in the chain. The tension in the chain is going to be our gravitational force, 833 newtons, minus our buoyant force, which we just calculated to be 100 newtons. And this gives us an answer of 733 newtons. The answer that's closest to this is going to be answer choice B. So the correct answer to problem 2 is going to be B. Fantastic. Let's move on to problem 3. Problem 3 says, 2 wooden balls of equal volume but different density are held beneath the surface of a container of water. Ball A has a density of 0.5 grams per cubic meter, and ball B has a density of 0.7 grams per cubic centimeter. When the balls are released, they will accelerate upward to the surface. What is the relationship between the acceleration of ball A and ball B? Now, the net force on each ball is going to be the difference between the buoyant force and the gravitational force. And so we can write that the net force is going to be equal to F buoyant minus F gravitational, and that's going to be equal to mass multiplied by acceleration using Newton's second law. Now here, we can expand on both of these terms. The buoyant force is going to be the density of water multiplied by the volume of the ball multiplied by acceleration due to gravity. The buoyant force is actually going to be equal for both balls because the volume of both balls are equal. They're the same. And so the buoyant force for each ball is the same. What about our gravitational force? This is going to be equal to mass multiplied by acceleration due to gravity. Since the two balls have different densities, That means that they're going to have different masses, which means that the gravitational force for each ball is going to be different because the densities of the balls differ. Here it becomes important to note that the ball with the smaller mass experiences the greater acceleration. Because both balls have the same volume, the ball with the smaller density has the smaller mass, and that is ball A, which means that ball A has the greater acceleration, and the correct answer for problem 3 is going to be answer choice A. Next up, we have problem 4. Problem 4 says, water flows from a pipe of diameter 0.15 meter into one of diameter 0.2 meter. If the speed in the 0.15 meter pipe is 8 meters per second, what is the speed in the 0.2 meter pipe? To solve this, we're going to use the continuity equation, which ensures that the flow rate remains constant when the fluid moves through different cross-sectional areas. The continuity equation for incompressible fluids like water is given by the following equation. A1V1 is equal to A2V2. Here, A1 is the cross-sectional area of the smaller pipe, and V1 is the velocity in the smaller pipe. A2 is the cross-sectional area of the larger pipe, and V2 is the velocity in the larger pipe. This equation tells us that the product of the area and velocity at one point in the pipe, that must equal the product of the area and velocity at another point. In other words, the amount of water flowing through the smaller pipe per second must be the same as the amount of water flowing through the larger pipe per second. Now, what we're dealing here with is the pipe, and the pipe is going to have a cross-sectional area that's equal to the area of a circle. The area of a circle is equal to pi r squared, where r is the radius of the pipe. Now, in this problem, we're not given the radius. Instead, we're given the diameter, but that's okay because radius is equal to diameter divided by 2. So we can go ahead and replace this radius term with diameter divided by 2. So we have pi multiplied by diameter divided by 2 squared, and this gives us the area of a circle to be equal to pi diameter squared divided by 4. And we're going to go ahead and take this term and replace our area 1 and area 2 terms with this expression. That gives us V1 multiplied by pi diameter 1 squared divided by 4. That's equal to V2 multiplied by pi diameter 2 squared divided by 4. Now, our ultimate goal here is to calculate the speed in the 0.2 meter pipe, which means we're solving for V2. Before we isolate this variable, let's just take a look at this form. On both sides, we have this pi over 4 term. Since it appears on both sides, we can go ahead and eliminate it. What we're left with is V1 multiplied by D1 squared is equal to V2 multiplied by diameter 2 squared. We're trying to solve for V2, so we can go ahead and isolate that variable. That gets us V1 multiplied by D1 over D2 squared. And we actually have all of these variables, so we can go ahead and start plugging things into our equation. V1 is equal to 8 meters per second squared. This is multiplied by D1 over D2, which is 0.15 divided by 0.20, and that's all squared. Now we can simplify what's inside this parentheses here. 0.15 divided by 0.20, this is equal to 3 over 4. And that's easier to think about squaring. So here we have 8 multiplied by 3 over 4 squared. This gives us 8 multiplied by 9 over 16. Here, 8 and 16 are both divisible by 8, so if we divide both of these values by 8, we get 1 over here and 2 over here, and we're left with 9 divided by 2, which gives us 4.5 meters per second. And so the answer for problem 4 is going to be C, 4.5 meters per second. Wonderful. Let's move on to problem 5. Problem 5 says a hydraulic lever is used to lift a heavy hospital bed requiring an amount of work W. When the same bed with a patient is lifted, the work required is doubled. How can the cross-sectional area of the platform on which the bed is lifted be changed so that the pressure on the hydraulic lever remains constant? Now, this question tests our understanding of Pascal's principle, which states that a change in pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and to the walls of the containing vessel. Now, we're told that the work required to lift the bed with the patient is double the work needed to lift just the bed. In other words, the force required doubles when both the bed and the patient have to be lifted. To maintain the same pressure, we have to double the cross-sectional area of the platform of the hydraulic lever on which the patient and the bed are lifted. So the correct answer here is going to be answer choice A. The cross-sectional area must be doubled. Let's move on to problem 6. Problem 6 says, the figure shown represents a section through a horizontal pipe of varying diameters into which 4 open vertical pipes connect. If water is allowed to flow through the pipe in the direction indicated, in which of the vertical pipes will the water level be the lowest? Now, the vertical pipes, they're open to the atmosphere, and that means that atmospheric pressure applies uniformly to all of them. Therefore, the height of the water column in each vertical pipe is dependent on the hydrostatic pressure in the horizontal pipe. Now, as water flows through the horizontal pipe, it encounters sections with different cross-sectional areas. This is going to be important, especially when we consider the continuity equation, which states that the product of cross-sectional area and velocity must remain constant for an incompressible fluid. So according to the continuity equation, the velocity of the water increases where the pipe is narrowest, as that smaller area requires a higher velocity to maintain the same flow rate. This increase in velocity results in a decrease in pressure according to Bernoulli's principle. Bernoulli's principle states that where the fluid's velocity increases, its pressure decreases. This pressure drop at the narrowest part of the pipe causes the water level in the connected vertical pipe to be lower than in any other sections. So in this case, pipe 2 corresponds to the narrowest section of the horizontal pipe, and pipe 2 will have the lowest water level because it experiences the greatest velocity and the lowest pressure. And this is a phenomenon known as the Venturi effect. That means that the correct answer for problem 6 is going to be answer choice B. Beautiful. Let's tackle problem 7 next. Problem 7 says, the speed of blood in the aorta is much higher than the speed of blood through a capillary bed. How can this fact be explained using the continuity equation, assuming that we're interested in average flow and that there is no net fluid loss? Now, the continuity equation, it states that for an incompressible fluid like blood flowing through a closed system, the flow rate remains constant. Mathematically, the continuity equation is expressed as A1 V1 equals A2 V2. Here, A1 is the cross-sectional area at one point, such as in the aorta, and V1 is the velocity at that point. This is equal to A2, which is the cross-sectional area at a different point, such as in the capillary bed, multiplied by V2, which is the velocity at that point. This equation tells us that if the cross-sectional area decreases, the velocity must increase to maintain the same flow rate. And if the cross-sectional area increases, then the velocity must decrease. Now the aorta, it has a relatively small cross-sectional area compared to the total cross-sectional area of all of the capillaries combined. Even though each individual capillary is very small, there are millions of capillaries in the body, and together their total cross-sectional area is much higher than the cross-sectional area of the aorta. This difference in cross-sectional area has a direct effect on the velocity of blood flow. So according to the continuity equation, when the cross-sectional area increases as it does in the capillaries, the velocity of blood must decrease. On the other hand, in the aorta, where the cross-sectional area is smaller, the velocity of blood is much higher. So since we're assuming no net fluid loss, the same volume of blood that leaves the heart through the aorta must eventually pass through all of the capillaries. This means that while the velocity in the aorta is high, the blood moves more slowly through the capillaries because the total cross-sectional area is much greater and the flow must be distributed over many more pathways. The key reason that the blood moves more slowly through the capillaries than the aorta then is because the total cross-sectional area of all the capillaries combined is much greater than the cross-sectional area of the aorta. This difference in area results in a lower velocity in the capillaries according to the continuity equation. And this idea best aligns with answer choice C, which says that the cross-sectional area of all the capillaries added together is much greater than the cross-sectional area of the aorta. Again, the correct answer for 7 is C. Next up, we have problem 8. Problem 8 says, which of the following data sets is sufficient to determine the linear speed through an area of a rigid pipe? A says the cross-sectional area in another segment of the pipe and the cross-sectional area in the region of interest. Now, this would be sufficient if we also knew the flow rate in another segment of the pipe. Then we could use the continuity equation to determine the linear speed. But we're not given that, so A is not the correct answer. B says the Reynolds number, viscosity of the fluid, density, and the diameter of the pipe. Now, this could be used to determine the critical speed at which turbulent flow begins, but there's no indication that there is turbulent flow. So B is not the correct answer either. C says the radius of the pipe, the pressure gradient, viscosity, and the length of the pipe. Now, this is the correct answer. This information would be sufficient to determine the flow rate through Poisson's law, and then that can be used to determine the linear speed by dividing by the cross-sectional area, which can be determined easily from the radius as well. So C is the correct answer, but let's work through D as well. D says the absolute pressure and density. This data could be used to determine the depth of an object in a fluid, but not enough to determine the linear speed through an area of a rigid pipe. So again, the correct answer for problem 8 is answer choice C. Let's tackle problem 9 next. Problem 9 says an object with a density of 2 grams per cubic centimeter is submerged to a depth of 25 centimeters in a container of dichloromethane. If the specific gravity of dichloromethane is 1.33, what is the total pressure exerted on the submerged object? Now, the total pressure exerted on a submerged object is going to be the sum of the atmospheric pressure and the gauge pressure. This is going to be mathematically expressed in this way that says P total is equal to atmospheric pressure that's acting on the surface of the liquid plus the gauge pressure due to the liquid column above the object. Now here, the atmospheric pressure, this is equal to 1 atmosphere, which is also equal to 101.3 kilopascals at sea level. We have that value. What we want to calculate is the gauge pressure. We're not given that directly. This is going to be equal to the density of the fluid multiplied by the acceleration due to gravity multiplied by the depth that the object is submerged. Now, we have the acceleration due to gravity, that's just a constant, and we know the depth that the object is submerged, 25 centimeters or 0.25 meters. We need to figure out, though, the density of the fluid. We're not given that directly, but we're given just enough information to figure it out. We're given the specific gravity of dichloromethane. So we can use the definition of specific gravity to figure out the density of the fluid. Remember that specific gravity, this is equal to the density of a fluid divided by the density of water. So if we're trying to figure out the density of the fluid, that's just going to be the specific gravity multiplied by the density of water. We're given the specific gravity of dichloromethane. You should know the density of water. We mentioned this in lecture. This is a value you should commit to memory. So then we can go ahead and just plug values in to calculate the density of the fluid. This is going to be 1.33 multiplied by 1,000 kilograms per cubic meter. This is going to give us the density of the fluid, which is equal to 1,330 kilograms per cubic meter. Now we have all the values we need to plug things into this equation and calculate the gauge pressure. So here we have the density of the fluid. We're going to multiply this by acceleration due to gravity, 9.8 meters per second squared. And then we're going to multiply this by the depth the object is submerged, which is equal to 25 centimeters or 0.25 meters. We want it to be in meters so that our final answer has units of Pascal. Okay, so this way we're going to get units of Pascal. Now, how are we going to do this without a calculator? We're going to do some approximations here. I'm going to round this, well, really not round, but rewrite 0.25 as 1 over 4. I'm going to round this to 10 meters per second squared. And then I'm going to approximate this to 1,200. And the reason why I want to do this is because 1,200 divided by 1 over 4 or multiplied by 1 over 4 is a really easy calculation. That's just equal to 300. Then 300 multiplied by 10 gives us 3,000 pascals, which is also equal to 3 kilopascals. Now we know our atmospheric pressure, and we've calculated our gauge pressure. We can just plug this into the equation. 101.3 kilopascals plus 3 kilopascals gives us 104.3 kilopascals as our total pressure. And this best aligns with answer choice B. So the correct answer to problem 9 is B. Beautiful. Next up, we have problem 10. Problem 10 says a hydraulic system is designed to allow water levels to change depending on a force applied at the top of the tank as shown. If a force F1 of 4 newtons is applied to a square flexible cover where A1 is equal to 16 and A2 is equal to 64, what force must be applied to area 2 to keep the water levels from changing? Now, this problem really relies on Pascal's principle, which states that when pressure is applied to a confined fluid, it's transmitted equally in all directions. Mathematically, Pascal's principle tells us that the pressure exerted at one point in the system must be equal to the pressure exerted at another point. And pressure is defined as force divided by area. So we're going to use that to solve this problem. Force 1 over area 1 is equal to force 2 divided by area 2. And our goal here is to ultimately figure out what the force 2 is. We want to figure out what force must be applied to area 2 to keep the water levels from changing. So what we're going to do here is rearrange this equation to solve for F2. F2 is going to be equal to F1 multiplied by A2 divided by A1. And we're given all of these values, so we can just go ahead and plug it in. F1 is 4 newtons, A2 is 64 meters squared, and the area 1 is equal to 16 meters squared. Now you notice meters squared cancel out. Our units for area are going to cancel out, and that means that our final answer is going to have units of Newton. Now here we have 4 times 64 divided by 16. Something that I'm going to do here to make this calculation just a little bit easier is that I'm going to divide 16 by 16, that gives us 1, and 64 by 16, that gives us 4. And what we're left with here is 4 times 4, which is equal to 16. So our final answer is 16 newtons. The force that has to be applied to area 2 to keep the water levels from changing is 16 newtons, and the correct answer for problem 10 is answer choice B. Problem 11 says balls A and B of equal mass, shown below, are fully submerged in a swimming pool. Which ball will produce the greater buoyant force? The buoyant force is the upward force exerted by a fluid on a submerged object. According to Archimedes' principle, the magnitude of the buoyant force is equal to the weight of the fluid displaced by the object. Mathematically, the buoyant force is equal to the density of the fluid multiplied by the volume of the fluid displaced, which is equal to the volume of the submerged object, multiplied by the acceleration due to gravity. Now, the buoyant force depends on the volume of the object, because the larger the volume, the more fluid is displaced, and hence the greater the buoyant force. Looking at this problem, we know that ball A and ball B, they have equal mass. And from what we can assume, both balls are made out of the same material. Then just by visually inspecting, ball A has a larger size than ball B. This means ball A has a greater volume than ball B, assuming both balls are made out of the same material and fully submerged. Since we just said that the buoyant force is directly proportional to the volume of the object, ball A having a larger volume means it's going to displace more water than ball B. Therefore, the buoyant force on ball A is going to be greater than the buoyant force on ball B, and that makes the correct answer for problem 11, answer choice A. Beautiful, let's move on to problem 12. Problem 12 says, which of the following correctly describes blood flow through the circulatory system? A says that the flow rate is constant. This is incorrect. The flow rate through different sections of the circulatory system is not constant. It can vary in different parts of the system depending on factors like cross-sectional area and blood pressure. So A is incorrect. B says pressure created by the heart moves blood through venous circulation. This statement is also incorrect. While the heart generates pressure to pump blood through the arteries and into the capillaries, venous circulation relies more on factors such as the contraction of skeletal muscles, valves in the veins, and pressure changes from breathing to help move blood back to the heart. So the pressure generated by the heart alone is not sufficient to drive venous return, as the pressure in the veins is much lower than in the arteries. So B is also incorrect. C says the volume of blood entering and exiting the heart in a single cycle is equal. This statement is correct, and it's actually the correct answer for problem 12. In a closed circulatory system, the amount of blood that's entering the heart is going to be equal to the amount of blood pumped out by the heart. This is known as cardiac output, and it ensures that there's no net accumulation of blood in any part of the circulatory system. So C is our correct answer, but let's go over D as well. D says the resistance of an artery is greater than the resistance of an arteriole. Now, this statement is incorrect. Arterioles are the primary site of resistance in the circulatory system, not arteries. Arterioles are smaller in diameter, and they have muscular walls that can constrict or dilate, significantly affecting blood flow and resistance. So answer choice D is incorrect. The correct answer for problem 12 is answer choice C. Let's move on to problem 13. Problem 13 says a low-pressure weather system can decrease the atmospheric pressure from 1 atmosphere to 0.99 atmosphere. By what percent will this decrease the force on a rectangular window from the outside? Note, assume the window is 6 meters by 3 meters and the glass is 3 centimeters thick. Now, this question is a simple application of the definition of pressure. Pressure is equal to force per area. If pressure decreases by 1%, like we see here, going from 1 atmosphere to 0.99 atmosphere, and the area doesn't change, then what will happen is that the force will also be decreased by 1%. All the other information that's given to you in this problem is just extra information that you don't really need. You just need to remember conceptually the definition of pressure and how it's related to force and area. So the correct answer for problem 13 is going to be answer choice A. Beautiful. Let's tackle problem 14 next. Problem 14 says two fluids A and B have densities of X and 2X respectively. They are tested independently to assess absolute pressure at varying depths. At what depth will the pressure below the surface of these two fluids be equal? A says whenever the depth of fluid A is 1/2 that of fluid B. B says whenever the depth of fluid A equals that of fluid B. C says whenever the depth of fluid A is 2 times that of fluid B. And D says whenever the depth of fluid A is 4 times that of fluid B. Now, the pressure at a certain depth below the surface of a fluid, it's given by this equation right here, which says that the absolute pressure is equal to the atmospheric pressure plus this term, and this term is the density of the fluid multiplied by the acceleration due to gravity multiplied by the depth below the surface of the fluid. Now here we want to set this pressure equation up for both fluids. So we can set this up for fluid A and we can set it equal to that of fluid B because the problem is asking us at what depth will the pressure below the surface of these two fluids be equal. Now what we see is that this atmospheric pressure term appears on both sides. So if we subtract it from both sides, it goes away. Then we're just left with these two terms. And what we notice here is that the acceleration due to gravity also appears on both sides. So now what we can do is we can write that the density of fluid A multiplied by the depth below the surface of the fluid for fluid A is equal to the density for fluid B multiplied by the depth below the surface of the fluid B. And here we can go ahead and replace these density terms with X and 2X respectively, as we're given that in the problem. So what we get here is HA multiplied by X is equal to 2X multiplied by HB. And here it becomes clear that if the density of fluid B is twice that of fluid A, then the depth in fluid A will have to be twice that in fluid B to obtain the same absolute pressure. So this has to be equal to 2HB in order for this to truly be equal to each other, which means that the correct answer for 14 is answer choice C. And now we can move into our last and final problem. Problem 15 says, A water tower operator is interested in increasing the pressure of a column of water that is applied to a piston. The operator hopes that increasing the pressure will increase the force being applied to the piston. The only way to increase the pressure is to alter the speed of the water as it flows through the pipe to the piston. How should the speed of the water be changed to increase the pressure and the force? To answer this question, we have to remember Bernoulli's principle. This is a fundamental concept that relates the pressure and velocity of a fluid such as water moving through a pipe. Bernoulli's equation for a fluid in motion is given by this equation right here, where P is the pressure of the fluid, rho is the density of the fluid, V is the velocity of the fluid, G is the acceleration due to gravity, and H is the height of the fluid above some reference point. In simpler terms, this equation tells us that as the speed of a fluid increases, the pressure exerted by the fluid decreases. And as the speed decreases, the pressure increases, assuming the height remains constant. Now the problem, it asks us how the speed of water affects the pressure and force on the piston. According to Bernoulli's principle, when water flows faster through the pipe, the pressure in the fluid decreases. On the other hand, when the water flow slows down or becomes slower, the pressure increases. This relationship is important for this problem because the operator wants to increase the pressure applied to the piston, which means that the speed of water must be decreased. All right, and we can just fall back to our equation of force and pressure. Pressure is equal to force divided by area, or if you were to rearrange this, force is equal to pressure multiplied by area. So since the operator is trying to increase the force applied to the piston, and force depends on pressure, increasing the pressure on the piston will increase the force. And like we said, to increase pressure, the water flow has to be slower. So there needs to be a decrease in the speed. And that means that the correct answer for problem 15 is going to be answer choice B. How should the speed of water be changed to increase the pressure and force? We have to decrease the speed. And with that, we've completed our practice problem set. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.